Hello. So today I'll be finding a formula that can tell me the final velocities of two objects after a collision when they're only given the initial masses and initial velocities. So first thing we need to assume, and maybe I'll prove it in another video, is that a force versus time graph is symmetric. It's symmetric about t over 2. So if a collision lasts the time t, then the force versus time graph will be symmetric about half that time, half the time of the collision. It'll be symmetric at this point. All right. And yeah. Now that we know that, and at t over 2, it experiences the greatest force. So, and this is because of the formula kq1 kq2 over d squared. All right, because you can think of any type of collision as just protons repelling things away. Because if two objects get close enough, the protons between them will repel each other, and that's why they force each other apart like this. And it's all because of the electric, I don't know what it's called, or electrical particle formula or whatever. So it basically says the force between two objects that are colliding with each other is related with the distance and the magnitude of their electric charge. All right. Now, there's something I also need to discuss. Not only at t over 2, it experiences the greatest force, but at t over 2, the velocity of the first object equals the velocity of the second object. So let me give you a scenario. Let's say there's a big object m1 moving at a speed of v1, moving to a stationary object m2 that's smaller. Now, when they start to collide, m2 will pick up some speed because of the repelling force between the protons, and m1 will lose some speed. And this will come to a point where their speed, where they become as close to each other as possible. They become the closest they can be. And at that point, their velocities are the same. So they're as close as they can be. Now, why their velocities must be the same? Well, if the velocity of m1 is greater than the velocity of m2, then this will not be the closest distance, because if the velocity of m1 is greater than the speed of m2, m1 can still move closer to m2. But if their speeds are equal, that means they're moving at the same speed. They're not getting closer to each other. If you move at the same speed as something, you're never gonna touch it. But however, if the speed of m1 is greater than m2, m1 will get closer to m2. So hence, if two objects are at their closest distance, their velocities must be the same. And this happens at t2. So at t over 2, where the force is greatest, when the force is greatest, it implies that the two objects are moving at the same velocity or are closest. When the force is greatest, the distance is the smallest. So distance is smallest, and hence v1 equal v2. So remember this. At the halftime of which the force versus time graph is symmetric, the velocity of the first object must equal the velocity of the second object, because they can't get closer to each other, because this is the closest they can be. So hence they need to be, the velocities must be equal at t over 2. All right, so let me give the argument once more. So we know at t over 2 the force is the greatest, right? If the force is the greatest, the distance must be the smallest. If the distance must be the smallest, then that means the objects must be closest to each other at t over 2. And if they're closest to each other at t over 2, their velocities must be the same, because if one velocity is greater than the other, they'll either move away from each other or approach each other. But we said they're at their closest, so their velocities must be the same. All right. Now, so we have this formula, the conservation of momentum. And let's say in this scenario, the m1 is losing velocity, right? So let's say m1 loses a velocity of x. It's losing a velocity of x. Then what must v2 then equal? Well, if momentum is to be conserved, v2 would have to equal, well, let me see. m2, let's just call this v final 2. We want to find what v final 2 equals. So we can rearrange this. m1 v1 plus m2 v2 equals m1 v1 minus m1 x plus m2 vf2. Luckily, m1 v1 just cancels out with each other, so we get this m2 v2 plus m1x plus equal, or no plus, equal m2 vf2, and hence vf2 would just equal, let me see here, v2 plus m1 over m2x. And let's plug this back into that equation. So m1 v1 plus m2 v2 must equal m1 v1 minus x plus m2 v2 plus m1 over m2 times x. All right? Because of conservation of momentum. Now let me think, what's the next step again? All right, now let's say we're at times t over 2. This means v1 must equal v2. So at time t over 2, some of the velocity of v1 is already lost. And if we're looking at this scenario, so the speed of m1 is lost, the speed of m2 is gained. So at speed t over 2, some velocity is lost. So hence, v1 minus x must equal v2 plus m1 over m2 over x. Because at t over 2, like we said, the velocities must be equal. And that's the velocity at t over 2. All right, and this x is arbitrary, but you're right. Now we need to find we don't want these x's to stay here. We need to find a formula to get rid of these x's. So let me think. All right, I have thunk. And so this is at t over 2. Then what about at t? Then at t, the final velocity would be v1 minus 2x. And this equals v final 1. Or let's just call it v3. This equals v3. And hence, this would be, and hence v2 plus 2 m1 over m2x equals v4, or v final 2. Why I doubled it is because force is symmetrical with time. So if the first velocity loses a velocity of x at t over 2, then at t it would lose a velocity of negative 2x, because so this is the velocity it loses, right, at t over 2, and then it loses a further that, because it's symmetrical. So if it loses velocity of x, then at time t it would have to lose the velocity of 2x. You understand? Because at t over 2 it loses 1/2, at t it loses the other half too. So negative 2x would be the other half. And same with this. If it gains m1 over m2x velocity at t over 2, then at t it has to gain double that, because it only gained half of the maximum velocity it can have. Or not exactly maximum velocity, but it just gained half, all right? Now that we have these formulas, we can finally find what v3 equals. So v3 equals negative v1 minus 2x, right? Now, we want to separate x. Now, how do we do that? Let me think about that. How do you separate x? We need to isolate x first here. So how would we do that? Well, let's bring this down here. I'm gonna bring all the terms with x's on one side. Plus x equals v1 minus v2. I brought this to here and that to there, so we get this. And if we isolate x, we get v1 minus v2 over m1, m2 plus 1. I factored out x to get m1 plus m2 plus 1, and then I divided it to this side. Alright? And then we can plug in x back here. So let me rip this page out. Alright? So we know that v3 equals, my voice is messing up, v1 minus 2, and let's substitute x for that. v1 minus v2, m1, m2 plus 1. And we know v4 equals, well, v4 equals that, right? And we plug in x. v2 plus 2 oh, whoops. Okay, let's just plug in this first. Or, yeah, I did not need that parentheses there. Times, well, m1 over m2. Alright? And basically that's it. That's the final velocity in terms of the initial velocities and the initial masses. You could make these formulas, let me write this down first. You could make these formulas more prettier, but yeah, these are the formulas or final velocities. Oh, and this not only works for this case, it also works if the smaller mass is the one with the initial velocity, and it should work for all cases where momentum is conserved. So yeah, this is the formula of the final velocities, v3 and v4. Thank you. All right.